Hey everybody, welcome to Regression in JMP. We'll show you how simple and easy it is to create a regression model and evaluate a regression model using JMP. And we'll start with a simple example. So let's imagine that you would like to be able to assess the population levels of various fish species. And the typical way of doing this is to go upstream and to shock the heck out of the poor little buggers, count how many float to the surface. But there might be an easier way, especially if you have a dam with a fish ladder attached. So if you have volunteers that go out, the question is, can you come up with some estimate of the average number of fish that are spotted by the volunteers per hour, and then use that to predict how many total fish there are upstream? In other words, how many would you get if you were shocking them? And so to collect this original data, poor little fishies did have to be zapped. So we're going to see if we can spare future fish from this electrocution. So we need to create a predictive model, and there's one variable, an independent variable, that we are using to predict a dependent variable. Okay, so we're going to use a simple linear regression. So here is that same fish ladder data in JMP. We have 11 independent observations where we had a ladder measurement and then an upstream shocking measurement. And regression really is robust to deviations from normality. So we don't really have to worry about normality when we're running a regression, right? Because we're not necessarily trying to assess only significance. We're trying to build a model that's based on all of the relevant information, all of the observations that represent our population. And if our population is not normally distributed, we want to be able to represent that. So we're going to maintain our data and just go right into the Analyze Fit Model tab, because we are actually creating a linear model. And when we come in here, I know that I want to predict my upstream fish count, so that's my Y response variable. And the independent variable that I'm using to predict that is my ladder count. So now I should be able to run this model, and I am using a standard least squares regression. And I click on Run, and it's going to show me the simple correlation of my ladder count versus my upstream count. And then also, if I scroll down, my actual by predicted plot. So this is, if I use the equation I came up with, what did I predict would be the upstream fish count versus what was the actual upstream fish count. And a lot of the metrics that I want to use to summarize this equation are included right in the forefront for us. Here's our R-squared. So this is telling us how much the total variability in the response variable can be accounted for by our model. So that's pretty stinking high. We can see whether or not we have a significant model. So here's the p-value associated with that. If we come down to the parameter estimates, this is actually where the equation is held. So here is the intercept right here. That's our beta naught, 0.14. And then here is beta 1, that coefficient or the slope term that we use to multiply by our ladder count in order to make the prediction that we want. JMP also gives us that residual plot, so we can look and see if we have any outliers. But remember that with regression, it's not just about whether or not we have outliers, it's about whether or not we have high leverage points. So to figure that out, we might first just go and look at our relationship, and I see that there is one value that certainly doesn't seem to fit the rest of the observations. So I might want to go into my magic red triangle and ask to have those Cook's D influence metrics added to my data table for each of the observations. So I can click on Cook's D, and it seems like nothing happens, right? So don't be scrolling in here for Cook's D, because remember, Cook's D is giving us a value for every single observation, which means we have to go back to our data table to see it. And lo and behold, here is a new column added with our Cook's D influence. And there's not a set threshold to figure out whether or not you have a high leverage point. It's more comparing each observation to the rest of the set and looking for ones that are abnormally high. And holy mackerel, yes indeed, do we have one incredibly high leverage point. So we talked about whether or not you can take out high leverage points, and it really comes down to whether or not they're correct. So let's just assume that this is correct, that on one day there really were a lot of fish coming through the ladder, and there really were a lot of fish upstream. Maybe that was the migration day for the species of interest. Well, does this data reflect the typical population that we're trying to model? And you could argue that it doesn't, that these are really so much higher than everything else that we see. Maybe this is anomalous and not truly representative. So we could argue for taking that out. But the real test comes in how much the model changes if we remove it, or how stable our model is. So let's go and back to our output and see how stable our model is. Remember, we can use the press statistic to figure out stability. So if I come back to my magic red triangle and I come into my row diagnostics, I can ask for the press. And then tacked on at the very bottom is that press statistic. So that's the sum of all of the residual error when we jackknife every single one of our observations one at a time. And then this is the mean of that. So on average, how far off are our jackknifed residuals? And we're seeing about 47. And since we're talking about fish and it's the same units as our response, this means that when we jackknife our residuals, we're off by about 47 fish. On average. How does that compare to our root mean square error? It is a heck of a lot higher than almost 7 fish that we have for our typical error in just the calibration data set. So this means we do not have a stable model. So that would be an argument for removing this high leverage point. The other way that we can test whether or not we should remove the high leverage point is to see how the model changes if we do remove it. If the model doesn't change, then it means that this really is representative of the relationship that we see in the rest of the data anyway, so it might not hurt to leave it. But if the model changes significantly, then it really would argue for us taking it out, because it means that this one point is essentially driving that whole relationship. So the way that we can figure that out is just by rerunning our model. Because JMP is so easy, I can right-click on this, and if I highlight this point, I should be able to exclude it. And just so we know that we've excluded it, let's also color it so that we can see it, but maybe it's not in there anymore. And then I can come up to the magic red triangle, and I can ask to rerun this script, right? Redo the analysis. And so it now opens up the exact same information that we have open in our regression model, but this time without that one observation. And it does look indeed very different. How do our diagnostics change? Wow. Okay, well, our R-square went down from 0.99 to 0.2. We no longer have a significant model. Probably not very useful for a model whose entire goal is to replace the upstream counts. So I'm sorry to say that I think we do need some additional data, maybe to fill in, if we go back to that other model, maybe to fill in this range between those very low fish counts, maybe when migration wasn't happening, and that high fish count. There's clearly something going on in between here. And if we could fill that in, we might have a more robust model. So I would have to summarize. This is saying that it's not possible to predict upstream fish counts based on ladder counts with the data that we have available to us. But let's now do a more complicated multiple linear regression. One of the fastest growing career fields globally is for statisticians, and that's because there's a lot more application even than just science for statistics. And here's a perfect example. So there is an outdoor adventure company who takes people up Mount Everest, and of course to do that you typically have to have people on oxygen to be able to make that hike. But we don't want to have to pay more Sherpas than necessary to carry oxygen tanks up that we won't need, or that maybe would encourage people to use more oxygen than they actually need. And we certainly don't want to bring up less oxygen canisters than we need, because then people might die, and that's bad for business too. So imagine you're the statistician that's been hired as a consultant for this company to figure out exactly, or be able to approximate roughly, how much oxygen each hiker might need to climb Mount Everest. So you've got some volunteers from the current group of climbers who have provided you with all sorts of biometric information. We know their general fitness. We put them through a test and we figured out how quickly they could run. We have their weight. We know their running pulse. In other words, what's their maximum pulse rate. We know their resting pulse rate. We know the maximum pulse rate that they've sustained during the training. We know their gender and we know their age. So the question is, can we use these sort of fitness and personal characteristics to predict how much oxygen they will need? And we had 31 different individuals volunteer to go through this testing. And again, we're really trying to predict this oxygen usage right here. This is our response variable, and we have all of these different potential independent input variables. It doesn't mean that we're going to use all of them. We have to figure out which ones really are significant and which ones in combination can be used to best predict that oxygen use. And notice also that we have a non-continuous variable here. We have this categorical variable of females and males, which we can still include in our regression by assigning either of these groups either a 0 or a 1. So let's go right into our fit model platform, and we're trying to predict oxygen, and we have all of these different variables that we want to test and see whether or not they're any good. Now, I don't need these Cook-D. You can tell I've already been into this data set looking for high influence points. But let's just assume that right now we're running it based on the original input information. So I'm going to add all of those to our model and run that. The output that we're going to get is very similar to that factorial ANOVA, right? We have the overall model with the actual by predicted so that we can see how well our predictions work, whether or not we have a linear relationship, and start to think about whether or not we have any outliers, maybe high leverage points. But because we have multiple variables here, we also have each of these broken down by their leverage individually. So we could examine each of these individual variables on their own as well. But typically, we only do that for the ones that are significant. So we need to figure out which of these variables were significant. So before I even go in and start evaluating this overall model, I want to look at which of my variables were significant, because I may be overfitting this data, right? So anything that's not significant, I want to pull it out. I don't want to have it in there sort of mucking up my variability calculations if it's not significant. So I can see right off the bat that there are several that aren't. But the thing that's really interesting is that each variable that's in this model, because it's accounting for a certain proportion of the variability, if you take it out, it actually alters what proportion the rest of the variables are accounting for. So each time you remove or add a variable, it can change the significance of the other variables in there. So I only want to take out my terms one at a time. So I'm going to start with the least significant variable. So it seems that this resting pulse is really the least significant term out of all of these. So I'm going to start by taking that out. So let's go back to our model, and shoot, I didn't keep the model open. Hang on a second, I'll show you how to do that. Okay, so when I'm doing this sort of data mining, I do want to try to keep this whole model window open so I don't have to keep rebuilding it. And I can do that by just clicking on this Keep Dialog Open box. Okay, so here we are back with the original, but we determined that resting pulse was really not significant. It was the least significant. So I'm going to remove that, and I'm going to rerun my analysis. And so now I'm going to come back down and evaluate each of those variables. And I still have some non-significant variables. It looks like the next one that's the least significant is weight. So I'm going to go back and pull out weight and remove that. I'm going to run it again. Okay, and this time if I go back down through, I still have some non-significant variables, and it looks like it's actually the gender that's non-significant. Again, note here's how the dummy variable comes in. It seems that in this case the males were assigned a 0, which means they don't need an estimate because anything times 0 is 0, so they're not in the model. But if you're a female, you would add 0.658 to the equation. That's if it were significant. It's not significant, so I'm going to go back and I'm going to pull that sex out and rerun again and see how significant my all of my variables are. And now look, another term has basically fallen out of significance. So I'm still going to pull out just the next least significant variable, and it seems that it is age. These are really close though. Holy mackerel. When it's close like that, I like to bring in another metric to help me figure out which one I should use. So remember I was telling you about the variance inflation factor, which helps you identify whether or not you have autocorrelation among your independent variables. If I right-click in this parameters estimate box, I can ask for additional columns. And right here is that variance inflation factor. So the general rule of thumb is that anything that's under 10 is usually fine, but the higher the variance inflation factor, the more likely that it's autocorrelated with another variable in your model. Because age and max pulse are both really close in terms of their significance, they're both borderline, but that the maximum pulse is much more closely correlated with the running pulse, I actually might choose to take out the max pulse, which is not necessarily the highest p-value, but close, because I can see that it's almost to that 10 cutoff for high variance inflation factor. So I'm going to go back in and remove that max pulse and see how that changes my age term. I run it again, and now I can see that, holy mackerel, well, look at that. Everything is significant now, including age. So that's a perfect example of how which variables are in there really influence the other variables that are also in there. I can right-click and check again to make sure I don't have any autocorrelation, and now you can see all of those really are quite low, so I'm happy that I don't have autocorrelation in here. I have a significant overall model. This model is accounting for about 80% of the total variability in oxygen used. My root mean square error is a 2.4, which is a really small proportion of the mean response. So the error is actually pretty low. I'm actually doing a very nice job predicting here. If I want to see how robust this would be, if I had new people coming in to apply this equation to, I can come back in and I can ask for that press statistic, and I can see my press root mean square error is 2.58, which is very close to my root mean square error of 2.45, so I have a robust model. So I could say that with these three terms, age, your running time, and your running pulse, which are really both getting at fitness, can be used to determine how much oxygen you would need. The question is, do I have any high leverage points? I still have to think about that. It doesn't necessarily look like it, but I could test for that. If I come back up and I ask to save my columns, and I ask to have those Cook's D influence terms saved back to the model. So you can tell I've done this quite a few times. So with this current regression model, the Cook's D influence is going to change depending on what model you're using. But for the current model, it looks like most of these are below about 0.2. When you have a lot of observations, it's hard to eyeball all of these numbers. So what I typically do is I actually analyze the distribution of that Cook's D, and it's going to automatically show me if I have any outliers. So I can see that I actually do have 1, 2, 3, maybe I got 4 what seem to be extreme values in terms of their distribution. This one in particular really concerns me. So I would go back in and let's just change the color on this so that we can see who this is. So I've just colored it, which means if I come back into my model, I should be able to see who that is. So it's actually not being predicted that poorly, but it is a high leverage point. So what I might try is rerunning this model. Let's assume that the data is good, but I might want to rerun this model with that value excluded. So let me go back and rerun this and see if the model changes with the removal of that high leverage point. I'll redo the analysis, and what I see is that I still have the same R squared. I still have a significant model. The only difference is that now age is no longer significant. It's still borderline significant, but not really making that cutoff. So that high leverage point would have me remove age, whereas with that high leverage point in, age stays. Now in this case, I might actually keep that leverage point out and go with this model. Remember that general rule of thumb for overfitting, that you don't want to have any more than one term for every 10 observations you have. So I could technically have 3 terms, which I do, 1, 2, 3, because I have 30 observations. But if I wanted to be more conservative, I might say, you know what, maybe I should go with 2. This is basically right on that threshold of what might be considered overfitting. So I guess it depends what my stakeholder who hired me to do this analysis really wants. If they'd rather be able to utilize more information and feel more confident in their predictions, then I might keep age in there. If they wanted the simplest equation and not have to ask clients for their age, which maybe the clients lie anyway, then I could give them the 2-term regression model. So in all, what I'm saying is it's really up to me as the statistician in consultation with the stakeholder who hired me to figure out what model is best. So I think, what am I thinking? I think I'll just keep it. It's your call. Are you seeing how statistics can be an art as well as a science? The key is, as long as you are transparent in what you do and you are describing this model fully so that someone else could decide whether or not they wanted to use that, that's what really matters. So I'm going to say that I have a 3-term model. I would report the intercept and the slopes for each, or the coefficients for each of these terms. I would report how significant each of those terms are. I would say I don't have to report the exact variance inflation factor, but I could say that variance inflation factor across all model terms was less than 2. That's a nice, quick, and easy way to say you don't have autocorrelation. I think I have a pretty meaningful model that's off on average really only by about 5%. And that 2.4 is about 5% of the mean response. And I think this is going to be a robust model. In other words, when I have new data points coming in, new people, I think this will work on them as well as the ones that were just used in this calibration. And I would interpret that. Do I think that this company can actually use this equation? I think they do, but I would tell them to incorporate, at least 5% error, right? Because that's how much I know I'm off by average. So incorporate at least 5% error, maybe overestimate 10% how much you think someone's going to use. So use this equation, add 10%, and you should be safe. That's what I would tell my client. So hopefully that's been a nice, clear introduction to simple linear regression and multiple linear regression in JMP. Enjoy!